Okay, the problem is search in a 2D matrix and 2. Okay, so the statement is write an efficient algorithm, okay, that search for a value that will be target in M cross N matrix. Okay, so this matrix has some properties, and basically the properties is all the integers in each row are sorted in ascending order from left to right, and all the integer in each column are also sorted in the ascending order from top to bottom. Okay, so basically this is example. You can see this is 5 cross 5 matrix. So according to the statement, all the elements, like row wise, all the elements sorted. You can see, okay, for this matrix all the sorted row wise. This row is sorted from left to right, this is also sorted from left to right, and this is also sorted. And you can also see that all the columns are also sorted from top to bottom. So this is sorted, this is sorted, and so on. Okay, so basically we are given this matrix, like we are given M cross N matrix, and we just need to find the target value. So for this example, you can see that our target is 5, so 5 is here, so it will return simply true. Okay, and for this example you can see the target is 20, but in this array we don't, in this matrix we don't have 20, so basically we need to return the false. Okay, now let's figure out some algorithms to find, to solve this problem. Okay, okay, so this is the first example we have. This is the 5 cross 5 matrix, and you can see, every row is sorted from left to right. So if this row is sorted from left to right, this is also sorted from left to right, and so on. Every row is sorted from left to right, and every column basically sorted from uh, top to bottom. Okay, so the very first approach that you can figure out, that is the very brute force approach, right? So this is a matrix. So basically you can search, you can iterate through all the elements of the matrix, like first of all this one, then you can check with this one, this one, this one, and so on. You can find the target value 5. Okay, so this is a very brute force approach, like you need to just search every element in this matrix, and for this you need to spend big of, you need to spend big of M and N complexity, right? So the complexity will be M cross N. Okay, so this is not a very good approach or very good time complexity for this problem. Okay, now let's try to figure out some other algorithms to solve this problem. Okay, so basically as we know that this row is, I mean, every row is sorted from left to right, right? So if as every row is sorted, so somehow you can think of, binary search, okay, to apply every row to find whether the target value is available on the on a particular row or not. Okay, so basically I'm talking about, first of all, let if we want to apply the binary search for this row, then we'll able to see there the target is not available in this row. Then we can also apply the binary search in this row. Okay, so you can see that the target is available. Okay, so in that way we can find. Okay, so basically you can, for this example, the target is here. Let's say our target is 26. Okay, so for that case we'll be applying the binary search, this row also and this row also, and all the way towards the last row. Okay, so for this case, if you want to apply the binary search to binary search to every row, then we need to spend, for every row we need to spend, uh, log of m. Okay, so for each row we need to spend, log m algorithms, a complexity. So overall time complexity will be n into log m. Okay, so this is the overall time complexity if we want to apply binary search to solve this problem. Okay, and this is also not a very optimal solution for this problem. Let's talk about the very optimal solution for this problem. Okay, so now notice one thing for this spatial matrix. So this is sorted row wise and also sorted column wise from top to bottom. Okay, now let's analyze this point. Okay, this corner. Okay, if you notice carefully, this is one. Okay, if we go downwards, you can see this is 2, this is greater than, okay, this is greater than this one. And if we want to go right, then you can see this is 4. Okay, so this is also greater than 1. Okay, so we can't decide whether we need to go right or down. Okay, now let's analyze another point. Okay, now let's analyze this corner. Okay, so now you can see that if you want to go downwards, you can see this is greater, okay, greater than 15. And if you want to go left, then you can see this is less than. Okay, so yeah, this can be a point. Okay, we can start searching from this corner. Okay, our target value actually. Okay, and if you also want to explore this corner, okay, so you can able to see that all the elements to the right of this will be greater, and all the elements to the top, okay, uh, will be lesser. Okay, so these are the two critical corner, you can say two special corner, you can start searching the target value. Okay, so now let's discuss the algorithm more briefly, more elaborately. ठीक है? Okay, so we have target. The target is 5. Okay, so we'll be starting from this corner. Okay, so now our current element, the current value is 15. So this is greater than our target value. So we need to go leftward, right? Because we need to find the lesser value, target is lesser. So we need to go leftward. So you can see this is 11. So still this is greater than our target value. So for this case also we need to move towards the left. Okay, so left, move one step left, so you can see we'll be getting like 7. So this is also greater than our target value. Now let's one step left. Okay, now this is 4. You can see now our current value is lesser than the target value. Okay, as it's lesser, so we need to move towards down, right? If we move one step down, you can see this is 5, and this is exactly equal to the target value. Okay, so you can say we got the target value. You can directly return the true value in this case. Okay, now let's discuss the second example with the same algorithms. Okay, okay, so this is the second example we have, and you can see for this example our target is 20. Okay, so we need to find 20 in this matrix. So if you notice carefully, you are not able to find 20 in this matrix because 20 is not available in this matrix. So in that case, we need to return false. Okay, now apply the same algorithms. Okay, to understand the algorithms more better way. Okay, so we'll be starting from here. Okay, so this is 15. So now our target is 20. Okay, so the current element is lesser than our target, so we need to move the downwards, right? So let's move one step down, so you will have so right now we're getting 19. So now it's still lesser than our target, so now move one step down also. So now this is 22. Okay, so now we can see that our target is 20, but this is greater, right? Our current element is greater. Now let move one step left. Okay, so this is 16, our current value is 16. Now this is lesser value, so now let's one step down, move one step down, this is 17. So still this is lesser. Then now also we need to move downwards. Okay, so this is current values right now 26. So this is, you can say this is bigger, right, than our current value. So we need to move towards the left. Okay, so now move one step left. So this is 23. You can say still it's bigger than our target value, so we also need to move one step left. Okay, so now let's move one step left. Okay, now this is 21, still it's bigger. So now let's one more step towards the left, so you can see now this is 18. Now the current value is lesser than our target value. Okay, so to find the greater value we need to move towards the down. Okay, now if we want to move towards down, you can see I am out of bound for this matrix. Okay, so in this case you can say that our target value is not available in this matrix. Okay, that's why we're out of bound. Okay, we are out of bound means target value is not available, so you can strictly return the false value for that kind of cases. Okay, now let's jump to the code section so that we can understand more better way and we can start coding. Okay, okay, so now we'll be starting the coding. Okay, for the optimal solution. Okay, now we'll start coding the optimal solution. Okay, so we already analyzed the algorithm. Okay, so we just need to start from either this corner or this corner. Okay, I'm starting from this corner. So this corner means this is the first row and this is the last column. Okay, So we just need to take two variables, two iterator you can say. So let's say this is int I will be the way declaring the denoting the very first row, that will be 0. And for the last column, let's say this is a, and this will be last column, right? So matrix of 0 dot length minus 1. Okay, so this is the two this is the two pointer, okay, for this, because we need to start from this index, this corner. Okay, now let's initialize the condition while loop. Okay, so basically at max we can go all the way towards the last row and all the way towards the first column, because we're starting from here, right? We're starting from the very first row and the very last column. Okay, so that's why the condition will be very simple. So I'll be less than the less than total length, that is matrix dot length, and column, because I mean j will be greater than equals to 0. Okay, so that is the condition. It's very simple, because at max we can go the last row and the first column. Okay, that's all. And every time we just need to check that if this current element is equal to our target value or not. So that will be very simple. If current element means matrix of I j, if this is equal to our target value, then we will simply return true. Okay, and otherwise let's assume the case that our current value is greater than the target. Okay, so if matrix of I j, okay, okay, my bad, it's I and j. Okay, suppose it's greater than the target. Okay, if this is greater than the target, then for that case you can see, if the current element is greater than target, then we need to move left towards right. So in that case the row will be constant but the column will decrease by one, right? So in that case we just need to do reduce the index of j by one, and simply. And else, okay, else the condition, in else condition the only thing possible is our current element is lesser, right? So in that case we need to move downwards, right? So we need to simply downward means the column will be constant and the row will be increased by one. So in that case we need to increase the I by one, and you can say this is capital, so we just need to change this small. Okay, so that's it. Okay, my bad, this is I. Okay, now this is good. And after all, when we'll be out of this loop, we just need to return the false value. So because we are out of the matrix, so there will be only possible reason will be there, the target is not available in the matrix, that's why we are out of the matrix. Okay, and if the target value is available, then we'll definitely find out through this loop. Okay, so that is the very simple code you can, and you can see. Okay, now let's run this code to check whether we are getting any error or not. Okay, and yeah, it's working very well, so we don't have any error. Now let's submit the code and check is it working or not. Okay, yeah, so it's get submitted, you can see. Okay, and that's it. So it gets submitted. Now let's discuss the time complexity for this algorithm. Okay, what will the time complexity? Okay, so if you notice carefully the second example. Okay, for the example where we have target 20 and we just need to return the false because 20 is not available. So just just notice carefully the the paths we actually covered. Okay, so we are started from here, right? And we move all the way, first of all down, then left, then down, then also left towards the very first column. Okay, so you can see at max we can travel. Okay, so at max we can travel all the row and then all the columns. Okay, so you can say the overall complexity will be the summation of row and the column. So the time complexity will be nothing but this will be nothing but big of my bad big of n plus n. Okay, so this will be basically the time complexity for this algorithm. And obviously we are not taking any space, right? So the space is basically the space complexity will be constant. Okay, yeah, that's it.